Hi students, I love you. Welcome to Suneel Engineering Academy. I am Sunil Kumar Bandaru. So many students requested that, sir, please start basic electronics through topic wise MCQs. So from today onwards, we are going to discuss basic electronics. Okay, if you have not subscribed this channel, please click on subscribe button and also please share these videos to your friends. Let us start the session, guys. Yes, coming to the first question. In the following, which is highest occupied band? Conduction, valency, energy band, and none. So in these two, valency band is highest occupied band. Is considered as highest occupied band. It is never empty, guys. Never empty. Why? Because it is filled with valency electrons. Filled with valency electrons. Valence electrons are nothing but the electrons which are present in outermost orbit. If you take any element, it has outermost orbit. In that some electrons are there. So valence electrons are always there. So it is never empty and you can say highest occupied band. So for example, if you take any one element, let us take silicon, atomic number is 14. So then 1s2, 2s2, 2p6, 3s2 and 3p2. So here what is the outermost orbit? The outermost orbit is the third orbit. In this third orbit, how many electrons are there? 2 plus 2, 4 valence electrons are there. 4 valence electrons are there. Okay. So if you can consider any element, the outermost orbit having some electrons always, so it is never empty and highest occupied band. In the same way, conduction band is filled with conduction electrons. It may be empty, or we can also say it is lowest occupied band. Very important question, guys. May be empty. Why? Because some of the elements may not participate in the conduction, so it may don't have conduction electrons. It is filled with conduction electrons, the electrons who participate in the conduction. Okay, for example, diamond may not participate in the conduction, that means may not allows the electricity. Okay, it don't have any conduction electrons. Okay, that means free electrons, it don't have free electrons, so maybe empty also. Okay, so highest occupied band is valency band, conduction band is the lowest. Coming to the next question, guys. In the following, valence electrons are bound tightly. Whenever the valence electrons are bound tightly, they may not allow the electricity. Which are not allows the electricity? Those are insulators. So we can say insulators, the valence electrons are bound tightly. Coming to the next question. In which of the following has least number of or no free electrons? Least number or no free electrons. Okay, in case of insulators, we don't have free electrons. So whenever there is no free electrons, then there is no electricity. Okay, so if you can consider any element, whenever we have some free electrons, the flow of those electrons, we have the current. Okay, for example, in our home, any one person is free, so we are always saying the work to that person only. Then he will move from that one from home to market or market to home, like that. That roaming, that movement is nothing but you can say current. So if we don't have free electrons, there is no flow of the current. Okay. As temperature increases, what happened to the resistance of semiconductor? So in case of conductors, the temperature coefficient of resistance, alpha is considered as temperature coefficient of resistance. It is positive. Positive in the sense R at T degree centigrade is equal to R naught into 1 plus alpha T. If this alpha is positive, then R at T degree centigrade is greater than R at 0 degree centigrade. That means as temperature increases, R T degree centigrade will be increases. That means as temperature increases, resistance will be increases. Okay, so that's why conductors are considered as positive temperature coefficient of resistance. Okay, in case of insulators or semiconductors, this alpha is negative. Whenever it is the negative means decreases. So that means as temperature increases, the resistance is decreases. So can say negative temperature coefficient of resistance. Okay, as temperature increases, the resistance will be decreases. So the answer is option B. Okay, as resistance decreases, then what happened to the current? Current will be increases. Okay, this is for pure semiconductor or intrinsic semiconductor only. For extrinsic semiconductor, that is different. Okay, coming to the next one. Extrinsic semiconductors are also act like a conductor. So those may have PTC, positive temperature coefficient of resistance. Don't worry, we will discuss those questions also. Coming to the next one. In intrinsic semiconductor, Fermi level lies dash. Fermi level lies dash. Here, in case of semiconductors, these are two types. One is pure and second one impure. Impure in the sense some impurities are added, some other materials are added, then it will become impure. Pure semiconductor is also called as intrinsic. Impure called as extrinsic. In this extrinsic, if you add p-type impurities, it will becomes p-type semiconductor. N-type impurities, it will becomes N-type semiconductor. Okay, so in case of intrinsic, the number of electrons, concentration of electrons is equal to concentration of holes. Both concentration is same. So whenever the concentration is same, then the Fermi level lies in between. Okay. So if you can consider it is a conduction band, always make conduction band on the top, valency band on the middle, at the bottom. Okay. So whenever the concentration of electrons and concentration of holes are same, or number of electrons is equal to number of holes, then this Fermi level may not attracted to any of the band. It will be in the middle. It will be in the middle. Why? Because here also same, here also same. So that's why it is in the middle place. We know very well, whenever we have equal and opposite force, that body is at standstill. Okay. So for example, if you have two jobs, what is conduction band job and valency band job? Both salaries are same. Okay. Then you are in the dilemma. You are in the middle. If conduction band is giving more salary, you will be attracted to the conduction band. If valency band gives a more salary, you will be attracted to the valency band. Correct? So in the same way, conduction band we have the electrons and valency band we have the holes. If the number of holes are more, it will be attracted towards the hole. If the number of electrons are more, it will be attracted towards the electrons. All of you getting idea about the Fermi? Okay. So this Fermi will be attracted wherever there is a more number. Okay. So intrinsic, both are same. Both are same means it is in between CB and VB. Okay. Coming to the next question. Energy gap at 0 Kelvin for germanium. This is the very important question, guys. Here energy gap is inversely proportional with the temperature, guys. That means as temperature increases, energy gap is decreases. Very important relation. Okay, so if you can consider for 0 Kelvin, in case of germanium or silicon, the energy gap for germanium at 0 Kelvin is, what germanium is 0.785 electron volt. Whenever this temperature increases from 0 Kelvin to 300 Kelvin, that means it will become room temperature. Then energy gap, as temperature increases, energy gap is decreases now. So it is 0.72 electron volt. Clear? So generally we are considering room temperature value, so that's why energy gap is considered as 0.72 electron volt. In the same way, silicon at 0 Kelvin 1.21 electron volt. As temperature increases, energy gap is decreases, so 1.1 electron volt. Okay, clear? All of you. So many students having doubt in this now. So temperatures for 0 Kelvin and 300 Kelvin. So note down these points. These are very important. Here they are asking 0 Kelvin. So high value 0.785. So the answer is option D. Okay. Coming to the next question. Energy gap at 300 Kelvin in case of silicon. In case of silicon, 0 Kelvin 1.21. 1.21, and for 300 Kelvin it will be decreases 1.1 electron volt. So the answer is option B. Coming to the next question. In the following, which is p-type impurity? Students, these type of questions are very repeated and very important in all the competitive examinations. What are the p-type impurities, acceptor impurities, n-type impurities, donor impurities? Okay, so I will give a small remembering trick to get idea on this. Okay, all of you listen carefully. P-type, n-type. Okay, so just remember in this method. P-type, P for P, acceptors. These are acceptor impurities. Okay, P for P. Here N for N, donor impurities. These are donor impurities. All of you clear? P type are acceptor impurities, N type are donor impurities. Generally we know semiconductor, either silicon or germanium, have how many valence electrons? Very important question. They have valence electrons are 4. Okay, valence electrons are 4. So in this case, if we add plus or minus 1 for this, then we can get higher number of holes or higher number of electrons. That means we have to add 4 plus 1 means 5, 4 minus 1 means 3. So we can add trivalent or we can add pentavalent impurities. Then we can get uneven, that means not equal number of holes and electrons. Okay, so here these are acceptors. Acceptors means ready to accept. Whenever they are ready to accept, whenever they have less electron, they ready to accept. Okay, for example, silicon or germanium have 4 valence electrons. If it has 3 valence electrons, then only they accept now. So these are trivalent. P-type impurities are, or P-type are trivalent. So trivalent, so that's why they are always ready to accept. Ready to accept. In the same way, donor, they are ready to donate. Ready to donate means always having some higher. So pentavalent. These are pentavalent. So 5 valence electrons. All of you clear? P-type trivalent, N-type pentavalent. Now coming to the example. Coming to the example. For P-type, the example is a big tree. Try na. Try for a big tree. So try for 3. So A for aluminium, B for boron, I for indium, and G for gallium. Okay, so these are the examples of P-type impurities. And coming to the N-type impurities, pen, Bapuji's pen. Pen. Bob. Who donate the freedom to Indians? Bob donate the freedom to Bapuji, donate the freedom to the Indians. So like that you can remember Bob. B for bismuth, A for arsenic, and again A for antimony and P for phosphorus. Okay, so in this way you can simply remember. And P, in the P type, P is a big hole, so majority carriers are holes and minority carriers are electrons. Okay, here N type, major N for electron, majority carriers are electrons, minority carriers are holes. We can also understand this one by the concept, but here in the MCQs discussing all the concept is taking a lot of time, so that's why I'm giving a simple methods to remember. Okay, once again guys, all of you close your eyes, just listen. We have P type semiconductors, N type semiconductors. Okay, P type, P for acceptors. So if they want to accept, there has to be less valency electrons than the semiconductor. So that means those are nothing but trivalent. So trivalent, tree. So tree means a big tree. Tree for big tree. So A for aluminum, B for boron, indium, gallium. Okay. So all these having three valency electrons. Okay. Three valency electrons. That means these silicon having 4, this trivalent having 3, so they accept one electron. Whenever one electron move from silicon to this trivalent, here one hole is created now. Here one hole is created. So many elements we have now. So many molecules we have. That means so many holes are created. So holes will be higher. So this will becomes majority carriers and remaining will be minority carriers. In the same way, N type semiconductor, N for donor. N for donor. If they want to donate, they must having one electron more. Okay, at least one electron more. So that means more than 4, that is 5. Pentavalent. So N type are pentavalent. Pen. Who donates the freedom to Indians? Bapuji. So BAP. Bapuji's pen. That is a remembering trick. BAP. B for bismuth, arsenic, antimony, phosphorus. Okay. So in this N type, what is happening? Here they are donating any that is any element if that donate the electrons, that donate one, then concentration of electrons will be increases. Okay, so then majority carriers will be electrons and minority carrier will be holes. Okay, minority carriers will be holes. This is in case of N type. So P type impurity, P type a big tree. So here A for aluminum. So the answer is option D. Coming to the next question, P type impurities. P type impurities, a big tree. Okay, so aluminum, boron, indium, gallium. Boron, indium, gallium, all given now. So answer is option D. Okay, like that you can give the answer. In the following, which is acceptor impurities? Acceptor, P type. Again, P type, a big tree. So boron, indium, gallium. So we can say all. In the following, which is N type impurity? N type, N for donor. Who donates the freedom? Bob. Okay, bismuth, antimony, arsenic, phosphorus. Phosphorus is there, so we can give the answer as phosphorus. Okay. In the following, which are N type impurities? Bob, bismuth, arsenic, antimony, all are there, so we can give the answer as D. In the following, which is donor? Bismuth, arsenic, antimony are donor impurities, so we can give the answer as option D. So if we know this simple concept, if they have given the question in any manner, we can give the answers. Okay. The P type semiconductor Fermi level lies. Just I said, this Fermi level always attracts wherever there is a more concentration. It will be attracts wherever there is more concentration. In case of P type, what are the majority carriers? Majority carriers, holes now. Minority carriers, electrons. So it will be Fermi level attracts towards to the majority carriers, towards to the holes. So here we have conduction band, here we have valency band. Okay, generally it is in the middle. for intrinsic. Okay, so in case of p type, the majority carriers are holes. Holes are exist in valency band now, so it will be shifted towards to the valency band. Okay, now the valency band having more money, so that's why it is shifted towards to the valency band. Shift to downwards, that is near to the valency band. Shift to downwards, that is near to the valency band. Okay, the same way if you can consider n type. N type majority electrons, minority holes. Okay, majority are electrons, minority are holes. So that means it will be shifted to majority carrier side. Majority carriers are electrons. Conduction band having electrons. Valency band having holes. So for intrinsic it is middle. Okay, now here the majority carriers are electrons, so it will be shifted towards to the majority carrier side. So that means it will be shifted upwards, that is towards to the bottom of conduction band. Shift upwards, that is towards to the bottom of conduction band. Okay, all of you clear? These are very important question, guys. Coming to the next one, semiconductor found by dash bonds. Semiconductor found by very strong bonds, that is covalent bonds. So the answer is option A. Coming to the next one, silicon and germanium contains how many valence electrons? I have already given silicon and germanium having 4 and 4, that is silicon having 4, germanium having 4. Gallium having how many free electrons? What is this question, sir? Whenever we are getting this question in the examination, so we feel that why they have given physics questions and all those. So here just think about this. Gallium, boron, indium, gallium, aluminium. So all these are nothing but, you can say, trivalent. Na? So trivalent means they have 3 valence electrons. So if they are asking gallium, we can directly give the answer as trivalent. Na? So no need of atomic number, no need of electronic configuration and all those. Okay, so whenever they have given the question on aluminium, boron, indium, gallium, how many valence electrons, simply you can use trivalent. Okay, the same way bismuth, arsenic, antimony, phosphorus, you can use 5 valence electrons. Okay, 5 valence electrons. Coming to the next one. When a free electron is recaptured by hole, that process is called as. Whenever that is electron is recaptured by holes, that process is nothing but recombination. That process is nothing but recombination. Barrier voltage VB will be dash. Here the barrier voltage VB depends on temperature. Depends on temperature. What is this effect of temperature on VB? VB is equal to minus 2 millivolt per degree centigrade. That means as 1 degree centigrade increases, temperature increases, VB decreases by 2 millivolt. Okay, so as temperature increases, VB will be decreases. As 1 degree increases means 2 millivolt VB will be decreases. So the answer is option D. Answer is option D. Okay, so we can also make VB is equal to minus 0.002 delta T. Delta T. Okay. Generally, leakage current, that is IC naught, double for every dash degree centigrade rise in temperature. IC naught will be depends on temperature, is a temperature dependent. This is generated due to thermally generated minority charge carriers. Thermally generated. Thermal in the sense they depends upon temperature. Minority charge carriers. Okay, so they are depend upon temperature. For every 10 degrees centigrade rise in temperature, I naught or IC naught, that is leakage current, will be double. Current double. Okay, so for every 10 degrees centigrade rise. Coming to the next question, leakage current in germanium, silicon devices in the order of dash. So the leakage current in case of germanium is in terms of microamps, and for silicon it is in nanoamps. Okay, so it is the very advantage of silicon, it has low leakage current. Sorry, the leakage current in germanium is microamp, in silicon nanoamp. Microamps and nanoamps in the sense, answer is option B. Okay, coming to the next question, guys. A very easy question. The process of adding pentavalent and trivalent impurities to pure semiconductor is called as dash. What is the process of adding pentavalent or trivalent? That is nothing but doping. In electronic terminology, we call it one as doping. Semiconductors are those substances whose electrical conductivity lies between conductors and insulators. In terms of energy band, valency band is dash and conduction band is dash. In the very first question I have given about this, valency band is almost filled and never empty. Completely filled, or you can say never empty. And conduction band may be empty now. All the elements may not allows the electricity. Okay, that means so many elements don't have conduction electrons, so that may be empty also. So almost filled, almost empty. So almost filled, almost empty. So the answer is option A. Okay, answer is option A. Coming to the next question, guys. Forbidden band is largest in dash. The gap between conduction band and valency band is nothing but, you can say, forbidden band, and this is greater than 5 electron volt for insulators. Okay, in case of semiconductors, this is for insulators. In case of semiconductors, this energy gap is approximately 1 electron volt. This energy gap is nothing but 1 electron volt. In case of conductors, conduction band and valency band overlapped. Overlapped in the sense no gap. No energy gap between those. Okay, so here is largest in case of insulators. After that semiconductors, after that conductors we don't have. That's why electricity can easily flow. Which of the following materials has more number of free electrons? More number of free electrons. If we have the free electrons, then current can easily flow. So in which the current is easily flowing? That is conductors. So we can give the answer as conductors. In conductor, we have more number of free electrons. Okay, coming to the next question. In an intrinsic semiconductor, there are dash. In the previous session, we have already discussed intrinsic in the sense that is pure semiconductor. In case of pure semiconductor, what I said, number of electrons is equal to number of holes. Okay, so equal number of electrons and holes. And in case extrinsic, extrinsic or impure. In this, we have two type now. One is P type and one is N type. P type, which are majority carriers, holes. That means holes are greater than electrons. Here, electrons greater than holes. And according to this, the Fermi energy will be shifted towards the hole side, that is valency band side. Here the Fermi energy will be shifted towards to the electron side, that is conduction band side. We have also discussed that questions. Okay. Forbidden energy gap in case of diamond. Yes, sir. If you are asking what is the forbidden energy gap in case of copper, in case of silver, in case of diamond, how can you the answer, sir? How to remember? This is a very simple logic in this, guys. If you know the type of material, it is a conductor or insulator or semiconductor. Okay, based on that we can give the answer now. If it is belongs to insulator, we can say the forbidden energy gap. This energy gap is greater than 5 electron volt generally. The diamond is the insulator now. Greater than 5 electron volt, we have one option, so directly give the answer. If the material is belongs to semiconductor, for example, if they are asking germanium, okay, so then it is in the order of 1 electron volt, so we can use that one, 0.7. Okay, so like that we can use the answers. Coming to the next question, guys. In a p-type semiconductor dash, already I have given in p-type, what are the majority carriers? Holes. Minority carriers? Electrons. Okay, so electrons are majority carriers and holes are minority carriers. No, it is for N type. Hole carriers are equal to electron carriers. No, it is for intrinsic. That is pure. There are only 4 carriers, no electrons, no. Holes are majority, electrons are minority. Yes, correct. So the answer is option D. Okay, so for example, if you have confusion in this, just make a small trick. I have also given a small trick in the previous. P, in the P there is a big hole is there. Okay, big hole is there. So majority carriers are holes, minority opposite. In the same way, N for electron. N for electron. Okay, so you can remember in N, electrons are more than holes. Okay, so that is a simple remembering trick. A semiconductor when placed at 0 Kelvin will be act as dash. At 0 Kelvin, the energy gap is more, so it may not allow the electricity, so it will be act as the insulator. Okay, semiconductor will be act as the insulator. Coming to the next question, guys. Which of the following has the highest mobility? Which of the following has the highest mobility? So the highest mobility is electron. Electron is small in mass. Its mass is very lesser. So that's why it can move faster. It can move faster. So the highest mobility is nothing but electron. The temperature coefficient of intrinsic semiconductor are just a semiconductor. If they are asking like this, intrinsic or just a semiconductor. For this, it is a negative temperature coefficient now, already discussed in the previous session. If they are asking extrinsic, that will be a positive temperature coefficient. Okay, a heavily doped semiconductor. Whenever you dope the semiconductor, it will become extrinsic. In case of extrinsic, it allows the electricity now. So that means whenever it allows the electricity, that means it will be act like a conductor. It will have conductor properties. That is, it have positive temperature coefficient. Okay, positive temperature coefficient. So the answer is option D, positive temperature coefficient of resistance. Coming to the next one, an extrinsic semiconductor has dash. Extrinsic in the sense P type or N type. P type or N type. Here what are the options they have given? More number of free electrons than holes, may be correct. More number of holes than free electrons, that may be also correct. Equal number of holes and free electrons, no. Either more holes or more electrons. Okay, more number of free electrons than holes. This is in case of N type. More holes, P type. Okay, but extrinsic semiconductor may be either P or N. So that means either more holes or more free electrons. This is the most suitable answer. So we can give the answer is option D. Extrinsic is in the sense it may be P type or N type. So maybe more holes or more free electrons. Electrical conductivity of semiconductor dash. Electrical conductivity of semiconductor is dash. This electrical conductivity of semiconductor is depends upon the temperature, okay, and generally this conductivity is proportional to temperature power 3 by 2. So as temperature increases, this conductivity also increases. So increases with rise in temperature. So the answer is option B. Increases with rise in temperature. So the answer is option. Coming to the next question, a free electron means dash. What is a free electron? Whenever, that is, if you can consider valence electrons, in that valence electrons, if any electron is not bonded with the other particles, then that electron is considered as free electron. Okay. So all electrons in the atom, no. The electrons not belongs to atom itself, no. Valence electrons which are loosely attached or not attached to the nucleus, that is nothing but we can say free electron. So the answer is option C. In an intrinsic semiconductor, Fermi level represents the energy with the probability of its occupation of dash. This is the definition of the Fermi level, that is nothing but the probability of the occupation is nothing but 50%. At least 50% probability. So the answer is option B, 50% or 0.5. The material that has highest energy gap at room temperature. The material that has highest energy gap at room temperature. So energy gaps are higher for insulators. High for insulators. Okay, in the order of greater than 5 electron volt. After that, semiconductors. So if we can consider here, all are like semiconductor type of device. In this, CDS having very high, that is 2.42. Okay, and gallium arsenic, cadmium stibbium having 2.42, gallium arsenic approximately 1.44 electron volt. Okay, and this germanium 0.67 and silicon 1.1 electron volt. So they have lot of energy gap for this cadmium stibbium and gallium arsenide. Okay, so these because of one of the reason of these having high energy gap, they can be used in case of LEDs. Okay, so cadmium stibbium is the answer. Answer is option B. Coming to the next question, guys. The current due to migration of charge carriers from higher density to lower density is called as dash. This is nothing but we can say diffusion. Here there is a two type of current takes place, guys, in case of electricity or in case of electronics. Okay, from the electricity, from the electrical, we can easily understand this one. In electrical, if the current want to flow, there must be a condition that whenever there is a potential difference, there is potential difference. Okay, that means whenever by nature By nature, if a conductor having here a 10 volt, here a 5 volt, now there is a potential difference is there. Due to that, the current is flowing by itself. Okay, that is like whenever the pipe is like in vertical manner, some angle, if you have some water, that is if you pour some water here, a little bit water, then water can easily move. Why? Because there is a height difference is there. Whenever there is a height difference, water can easily flow by its nature without giving any external force. Here also, whenever there is a voltage difference or potential difference, current can easily flow without any external force. And the second case, for example, if the wire is having like this, here 0 volt, here 0 volt. Now current flowing? No, current is not flowing. If you want to flow the current, then what you have to do? You have to connect one battery, then this positive will becomes 9 volt, this negative will become 0 volt. Now there is a potential difference. Now the current is flowing. Correct. That means here by external supply, the current is flowing. That means same like if the pipe is horizontal, there is no potential difference, then you have to connect a motor. Whenever you connect a motor, then it will create that pressure difference, then water can be easily flowing. All of you getting my point? So here, whenever there is a high potential to low potential, current is flowing. Higher the height to lower the height, current flowing. This is nothing but by its nature. Okay, this type of is nothing but in electronics. In case of electronics, this type of current is nothing but diffusion current. Okay, so whenever there is a difference in the charge carriers, okay, so that is here higher density, here lower density, the migration of charge carriers from high density to low density is nothing but diffusion. In the same way, whenever you apply external force due to electric field, the current is flowing due to electric field is nothing but you can say drift by external force. We know the drift irrigation system in the farming. Okay, that is from the pipe, the water is coming with a lot of pressure. Okay, that means drift. So that means whenever by applying a external force, or that is by electric field, if you are getting the current, that is a drift current. Okay, so current due to migration of charge carriers, diffusion. Current due to under the influence of electric field, drift. Due to electric field, drift. Okay, here so many students confused these two words, so that's why I'm giving this much of explanation. Okay, student, if you like my classes or my explanation, please encourage me with your likes and comments. Okay, coming to the next one, the current due to influence of electric field. Just now I have given, now no need to explain, that is the drift current. Okay, maximum operating temperature of silicon. Here, coming to the operating temperatures of the silicon and germanium, silicon have very wide operating temperatures. And germanium narrow operating temperature. So it may be minus 60 degrees to 175 degrees, or it may be up to 200 also. Maybe up to 200 degrees also. But coming to this germanium, it is minus 60 degrees to 75 degrees centigrade only. That's why, that is also one of the reason it is used very less in so many communication equipments, that is cell towers. Okay, so our data devices, in all those generally silicon is extensively used. Why? Because it can bear with the high temperatures also. Okay, sir, in summer, if you can consider maximum 50 degrees only, na, if it can be operate 75 degrees, then why it is not used? No, not like that. Okay, so not outside temperature. So whenever any electronic equipment is operating, then lot of power dissipation will be takes place. Then the temperature is very higher also. Okay, whenever any electronic device is operating within that circuit, if you touch your finger, then you can feel the temperature. Okay, it may be more than 75. Okay, so here silicon, and also one more reason silicon is preferred, because of main reason is its availability. Silicon is easily available, low cost. Okay, so silicon minus 60 to 175 degrees. And second advantage, it's less leakage current. Third advantage, high power handling capacity. So whenever the temperature values are more, it can handling more power. Operating temperature of germanium minus 60 to 75. The barrier voltage for silicon semiconductor device is dash. We know for silicon the barrier voltage is 0.7. In case of germanium it is 0.3. Okay. Coming to the number of atoms per density in case of silicon. In case of silicon and germanium, for germanium the number of atoms per density is 4.42 into 10 power 22. Okay, coming to the silicon, it is 5 into 10 power 22. So some more atoms we have in case of silicon. Okay, so silicon they are asking 5 into 10 power 22. Okay, under thermal equilibrium in semiconductor, the ratio of number of holes and number of conduction electrons. Under thermal equilibrium, the number of holes and number of electrons will be equal. So equal means the ratio is 1. The ratio is 1. Okay. Okay, students, we will discuss the remaining questions in the next session. And all of you, please subscribe this channel and also share the videos to all your friends. Okay, and if you want download the PDF, you can visit www.suneelengineeringacademy.com and follow the steps, and you can download the basic electronics PDF. Okay, okay, students, thank you.